nanohub.org.
Online simulation and more for nanotechnology.
Good afternoon, everyone, and welcome to this afternoon's lecture, the Arden Bement Jr. Distinguished Award Lecture. My name is Suresh Garamella. I'm the Executive Vice President for Research and Partnerships and also a Professor of Mechanical Engineering. It's truly a privilege to participate in this event for me. It's just wonderful to always hear about our faculty's work and the folks we recognize at these events are amongst our most decorated. So it's great to see that. This year marks the fourth year we've given the Arden Bement Jr. Award. This award was established by Distinguished Professor Emeritus Arden Bement and his wife, Mrs. Louise Bement. It recognizes annually a Purdue faculty member for recent outstanding achievements in pure and applied science and engineering. Arden Bement Jr. Award winners are nominated by their peers and approved by my office and then by President Daniels. We're delighted today to have the person in whose name we honor this award, who was the David A. Ross Distinguished Engineering Professor and now is in emeritus status. So let's all give a very hearty applause for Arden Bement. He would have won this award many times over had he had the award existed at that time. So I would also like to acknowledge anyone in the audience who has received either a Bement Award before or even a McCoy Award, because the McCoy Award has been around much longer. I know we have several in the audience. If you could stand, please, and be recognized. Andy Weiner, Supriya Datta, Lad. Very good. It's my pleasure now to invite, all of you to a reception right after this event. It's in the Ringel Gallery. Walk out the door and to your left. So please stay and congratulate our winner today right after this event. So I hope you'll join us there. And now I'd like to welcome to the stage the Don and Carol Cyphris Distinguished Professor of Electrical and Computer Engineering, Mark Lundstrom. As the nominator of this year's awardee, he will introduce Peide Ye, the Richard and Mary Jo Schwartz Professor of ECE, who's this year's recipient of this award. Mark?
So thank you, Suresh. It's a great pleasure to introduce my colleague, Peide Ye. Peide is the Richard J. and Mary Jo Schwartz Professor of Electrical and Computer Engineering. We were fortunate to bring Peide to Purdue in 2005, just as the Burke Nanotechnology Center was ramping up. He's an example of a new kind of multidisciplinary engineer and applied scientist. Professor Ye started out as an electrical engineer. He received his BS.EE from Fudan University in Shanghai. He then did a PhD in physics at the Max Planck Institute, where he studied low-temperature physics of electrons in a periodic magnetic field under the direction of Klaus von Klitzing, who received the Nobel Prize for the discovery of the quantum Hall effect. Next, he studied the physics of quantum dots at NTT Basic Research Labs. Then he returned to the U.S., where he worked with Professors Lloyd Engel and Dan Swee at Princeton on so-called Wigner crystals. Dan Swee received the Nobel Prize for his discovery of his explanation of the fractional quantum Hall effect. In 2001, Peide joined Bell Labs, which became Lucent Technology and then Agere Systems, and shifted his attention to applied science and engineering. When we brought him to Purdue, he was working on 3-5 transistors with a new deposition technique called atomic layer deposition. He had the foresight to see that this technique had great potential for producing novel electronic devices. In the 13 years that I've known Peide, there are 3 things that have impressed me most about him. The first is his ability to enter a field where progress has been stalled for a long time, to find a way forward and to reinvigorate the field. The second is his talent for discovering new materials that have great promise for novel electronic devices. Today, I think of him as much of a material scientist as an electrical engineer or a physicist. And the third thing is that he's a great colleague to work with. Would you please join me in welcoming Professor Ye?
So thanks, Raj and Mark, for this kind introduction and the good words on myself. Okay, it's really my great honor to receive this Bement award, and also I'm very humbled here to, give this distinguished lectures. Actually, as a Professor Bement, so as a profound material scientist and engineer, so we are also, research on the electronic materials and for the device applications, and hopefully can extend the Moore's law and even do some work beyond. So, and since the Moore's law in microelectronics is such an important topic, and it's very important for the technology leadership of US and even for the welfare of the human societies. So I was fortunate, actually, supported in this 15 years, near 15 years at Purdue by various federal funding agencies and private sectors to support this research. And Professor Bement held some very top, leadership positions at some of the agencies such as NSF, DARPA, and NIST. So in some sense, he already has supported my research work, here. So first of all, I would like, acknowledge these individuals really, really helped me from a teenager how to grow up to be a Purdue faculty member. So actually, once I was very young, actually, this is my physics teacher. So he really motivated me, interested in physics and science. And I was very fortunate, did my PhD in physics with some, and also postdoc research with some of the best scientists in the world. And once I moved to Bell Labs, Lucent, and Gears, so this is my manager there, and I was fortunately work with him, and also Professor Wang and Li had there helped me really understand the applied device field, and let me smoothly move from low temperature physics to become a device engineer. And I was luckily joined the Purdue near 15 years ago. So Raghu is our department head, and the whole ECE faculty is very supportive for my career. So I really appreciate. And also the Berkeley Nanotechnology Center. Ali is the director there, so we get a lot of help, a lot of support from this state-of-the-art facility by the staff members and the leadership. And of course, my colleague, back to Bell Labs, this is Ashar Afra-Alam. So he introduced Purdue to me and introduced me to Purdue, basically. So, and we have very nice cooperation even recently. And finally, not last, is my nominator, my mentor at Purdue, Professor Mark Planck Institute, not only to me, also to many young junior faculty at our area. So Mark is very supportive, every promotion, every, fellow, every award involved many supporter letters and a lot of work behind. I really, really appreciate. So, of course, I also appreciate, I'm lucky to have, many talented young students, postdocs working in my group. I cannot, some of them are also listed here, and I also have a lot of cooperations with the Purdue faculties in the different departments, colleges, and even worldwide. I have a lot of cooperation ongoing. And finally, I would like to support my family, particularly my wife, Jean. She really accompanies almost my whole life because she's my neighbor, also classmates from elementary schools. So, okay. So this is the outline of my talk. So I will first talk about what is the Moore's law in microelectronics. So then I will talk about our research work, how to, through the material innovation, structure engineering, and eventually device architecture, how to try to extend the Moore's laws. finally is the conclusion and the outlook. So this is the history of the computation. And from last century, 1900 up to now, maybe 20 times. So you can see that the x-axis is the x-axis is time year, and the y-axis is each calculation per second and per dollar, basically. So you can see this we get more and more computation and much cheaper. And why make this happen? This is a log scale. So this is, even in the log scale, it still looks like exponential increase. So this is mainly because the advance of the microelectronics. For example, this is the invention of the transistor, start of the transistor, and this is the invention of the integrated circuits would make it happen. So it's directly related what our area and what the Moore's law we want to talk about. So this is a Moore's law. Everybody know Moore's law in microelectronics. So x-axis is still year, start from, let's say, 1970, and until now is 16, 17, 18, like that. So the y-axis is the transistor density on per areas or on the chips. So Moore's law is from the 1965. So Gordon Moore is the co-founder of the big company now everybody knows is Intel. So this is not a physical law, it's just an observation. So he observe and predict. So the number of the transistor in per areas will be doubled every 1 year or 1.5 years. So the whole microelectronics industry development is pretty along this Moore's laws within this just 30, 40 years. So the issue is the mathematics. So once you double, like n the power, to the power of the n. So this is very, very big if your n getting increased. Okay. Let me give you an example. At the beginning of the chip, such as like we use it for the calculator. So the number of the transistor is around a couple of thousand. But today, so on the iPhone, the chips, your number of the transistor on the chip become 10 billion. So you may not still surprised from the calculator to become an iPhone. So I give you another example. So a lot of the graduate students here, every month you get $2,000 for the stipend to study at Purdue, right? So now you probably heard a couple of days ago, this mega lot is 1.6 billion, right? So so this is almost like a similar this number. Like you have the stipend 2,000 per month you got a mega lot every week. So you can see how amazing this Moore's law it is. However, if you zoom in these areas, you will see actually the Moore's law is not exponentially keep increasing. It is slowed down a little bit. Okay. Not as fast as we want or we wish. So this is our really research field. We want to extend the Moore's law and make our transistors cheaper, faster, and more functionality for the integrated circuit. So the issue is the power, and the power, because of power dissipations. So if you forgot breakfast, like the graduates usually do, you open a desktop nowadays. Because these are power dissipation in the integrated circuit, it's a very hot inside. You can cook your breakfast using your computer. So it's really eggs here. Okay, so it's very hot. So how to control the power, the heat, the dissipation of these transistors, these integrated circuits is the number one issue for our field. So the people did, like this the technology developer from Intel, for example, they use a strain silicon to improve the transport, and high K dielectric. That's something, the technique I research intensively. This is called atomically depositing. So you can see it's already commercialized, started from 2007. All your electronics in hands now, the mobile phones, everything is by the high K dielectric. And a couple of years ago, they used 3D structures. Sometimes we call FinFET. I will talk about these details almost around these transistor engineering with the time. Okay, so that's our research. So first of all, let's talk about the transistor. What means a transistor? Transistor, right? It's a three. So you always have a 3-terminal. Any transistor, you have only 3 terminals. So this is a typical transistor we are dealing with. It's a very simple, but it's a very complicated in general. So usually here we call it the source. Here we call it drain. So the electrons basically flow, millions, billions of electrons flow from the source to the drain through this blue color, this a piece of semiconductor. So then we usually have an oxide, an insulate on top of the semiconductor. So then we have a metal on top of this insulate oxide. So we use the electric field to control how fast, to control the flow of these electrons. So we have to use this oxide because we don't want the current, the electrons flow to the gate. So the gate to the source and the drain must be isolated. So the key is this involved metal, involved oxide, involved semiconductor. So sometimes we call it MOSFET. This is related with that. And it's include everything in the world, basically. This is 3 types of material we are dealing with for the electronic material. So that's why it's not that easy, because that interface and everything is really very, involved a lot of engineering work. So we are basically dealing with this transistor this is the electric field. Basically, look at all the transistor about is look at this electric field, because this voltage, how efficiently can control like this flow of the water, flow of the electrons, how can let it flow efficiently and let it close efficiently. So this is all about we are studying. So basically we are engineering this part, this very small part of the transistor. So include the materials, structures, and even architectures. So we are involved on my research at Purdue and even our areas. Basically, we are involved on the material research, 3-5 compound semiconductor, germanium, and nowadays 2D materials. And we are engineering in the material part, structure part, and the architecture part. And we are research everything here because of limited time. I just choose these, red star part. So in the material part, I just talk about the 3-5. In the structure part, I just talk about the germanium. In the architecture part, I just talk about the 2D materials. So that's the plan. So let's first look at the material part, 3-5. So what means 3-5? 3 means in the elemental table. So all these columns is 3. We call 3 column 3, column 5. So typical materials is like indium, gallium, basically out shell of the electron orbit. You just have extra 3 electrons. So that's why 3 coming from. 5 means in the column 5. So outside the shell is 5 electrons. Typical is arsenide. So 3-5 compound semiconductor is typical gallium arsenide as a semiconductor material, or indium arsenide or semiconductor material, or indium gallium arsenide as an alloy. Sometimes it happens. So what particular property of these 3-5 materials is this? We all know this 3-5 material have so-called a high electron mobility. Mobility means so how fast with certain kind of push, how fast you can move as an electron, as a particle. So the 3-5 material in general is much higher than silicon. For example, silicon, you may get a couple of hundred to 1,000, but the 3-5 material in general can be several thousand mobilities. So why mobility is so important? So we go to the fundamental transistor physics. So this is the plot. So the y-axis is called current. The x-axis is voltage. I remember I was taught by another Nobel Prize winner Horst Sturmer, he always say, he's a physicist, he always say, okay, if you do physics, you need to present all your results in one line. So then it's a simple way of physics. Okay, your experiment need all in the one line. But actually for the electrical engineer, we are even simple. If you think about the electrical engineer, all about it, it's just, we have just two things. One is current, one is voltage. So everything is about these two things. Okay, this is exactly, all the transistor is about the current versus voltage. So what I talk about, this current here is in log scale. So that's why if a MOSFET or a transistor working, so typically, silicon is the king of the everything, semiconductor. So the IV characteristics should be look like this. That's in log scale. So you can turn on the device, let's say 1 billion of electrons are flow from source to drain. But with just the gate, with the electrical field, you should very effectively can turn off the device by the order of 10 to 6 to 10 to 10 even. So this slope is very, very important to tell you how you can close down the device. Okay, so now if you have the high mobility as a channel, so your equivalent, like now your electron is much light, you can move it much faster. In this case, so at the same voltage, actually you can turn, once this device is turned on, you can get much more current. But that's not the whole story why we want to use 3.5 to do logic device. It's not only for the higher current than the silicon, but in real what we want to do is if you want the same current as silicon, you can see at the same level, because this is a log scale, so at the same level, your 3.5 device, you can turn on at the much lower voltage. So because you can scale down this voltage, so all the power dissipation in the logic chips in your integrated circuit is proportional to the voltage square what you supplied, this VDD. So because this scale down, so you are able to reduce the power, so you cannot cock your egg with your integrated circuit. So that's the motivation. But however, it's a beautiful kind of motivation for the research. However, there's a very fundamental bottleneck. So this is, you need to have a very nice oxide on top of your 3.5 compound semiconductor. So this is a topic almost 50 years. Okay, people are fighting with this fundamental problem for the long time, particularly from 70s and the 80s. There are a lot of research about how to form high quality oxide on compound, 3.5 compound semiconductor. It's a very popular topic in Japan, in US, in everywhere, in Europe, every research, device research field. But it goes through nowhere because it's really a very fundamental, difficult problems because, people are trying all kind of different methods about oxide formation on 3.5 compound semiconductor. Eventually, the field started to give up. This is even more crowded than nowadays two-dimensional material research, like, everywhere in the world. So, I'm kind of fortunate. I get at the beginning of 2000, I started to touch a new technique. This is called atomic deposition, this technique. So we are really, back to Bell Labs. So this is my colleague, Graham Wilk, and me and others. So, because at that time, so this commercial ALD tools is the first, it's invented in Finland and the first time employed at the United States at the Bell Labs. So we're able to use the commercial ALD tools to research on the 3.5. So this is the example. We realized at the very beginning, the high resolution TEM, you really can zoom in, look at. So after glow, these use the atomically deposition technique. I will explain in the next slide. So you can glow the high quality amorphous oxide on top of the gallium arsenide and without any visible, native oxide, all these issues you can see. Later on, we kind of understand that we call it a self-clean effect. And this is the ALD tools, we are used at the Berkeley Technology Center, and now more ALD tools are deployed there. And start from 2005. So this after, kind of we are pioneering work a couple of years. So this 3-5 MOSFET for the logic application become a worldwide hot topic, and many big industry, consortiums and leading groups in the device field all work on this particular topic. So what means atomic layer deposition is a very innovative approach. Actually, we know a lot of chemical vapor deposition or chemical reaction. You have chemical A and a chemical B. You start to react, become a compound, let's say C. So usually you put the A and the B at the same time, let it react. Then you grow the C. That's the usual approach. But the ALD is just to make this chemical A and the chemical B in the time scale separate. So we first purge, get the chemical A, get like absorbed on the surface of the substrate. Because it's absorbed, it can only cover the surface. So it cannot be grow to, it cannot put the second molecule on the top of the first molecule already absorbed by surface. Okay, so that's why it's a self-limited process. By the time 1, you put the chemical A on the top of the surface. By time 2, you get another chemical B inside, start to react to the chemical A. So eventually, you can atomically, by atomically, grow a compound C, such as aluminum oxide. So this is a self-limiting, because it's self-limiting process, it can be grow on 300 millimeter everywhere, as accurate as atomic layer. Really, the accuracy can down to astron thickness. And in the larger area, as I mentioned, this technique within 6-7 years. So it's really started commercialized, put in your integrated circuit and all your high-K dielectric nowadays use hafnium oxide is by this ALD technique. So we use this technique as my kind of group, I always identify my group is research on the ALD, and we cooperate with the Harvard group, Roy Golden, as a chemist. Eventually we can grow even beyond it. We not only can grow the amorphous oxide, we can even grow epitaxial single crystal oxide on top of the gallium arsenide, just like MBE, but we are grow at much low temperature. And the fundamental is a chemistry reactions, ALD. So you can have a very high quality interface on the gallium arsenide. So can you realize a very large current, inversion current as anybody else, this is probably 1,000 or even 10,000 high current. You really break these fundamental so-called Fermi level pinning issues on the gallium arsenide. And because the defect is so low, you can turn off the device also very effectively. So we usually call the substress slope. So you not only on and you can off, and you can do more. So you not only can transport with the electron, we can transport with the hole. So hole basically is a positive charge. Electron is a negative charge. So hole we usually is a positive charge. So you can also build up a positive charge in the transistors. We call the P-type transistor, PFET, connected the NFET and the PFET, and demonstrate the building block of all the integrated circuit. We call the inverter. So you can also make more complicated on gallium arsenide to make the logical operations. And even you can more complicated, you can usually we call the ring oscillator. So, this is really first time with the gallium arsenide, we can demonstrate all these circuit applications. So the key is the ALD, this technique. And even back to 2007 or 8 times, because we have demonstrated the first time, we can make the really high performance inversion kind of MOSFET on indium gallium arsenide. So even have a higher mobility. So that's why worldwide, so ALD become very popular, and the 3-5 MOSFET logic application research are spread in the industry and academia widely. Okay, so this is about material 3.5. Now I move to the second part. So this is about, we choose germanium as an example and talk about how this structure engineering is important. So now we make this not a planar, just a piece of semiconductor. We make some very, very small structures on the surface of this semiconductor to see how this effect. So if you take some courses from Professor Mark Landstrom or Professor Alam, you probably learn all these device physics about the scaling. So we are making the transistors smaller. Nowadays we are approaching this 10 nanometer or even 7 nanometer regions. So this is source and the drain. So they are so near each other. So that's why how the electric field can control this channel effectively become very challenging, because by this scale down, so this electric field can control the near the surface, maybe not control at far away from the surface. So that's why we need to do more engineering work. So the approach and the propose and eventually demonstrate is we make the structure. So for example, so if you cannot planar control underneath this semiconductor, so we make the semiconductor as a Y or make it much narrow. So you are not, the electrical field not control from the top or control everywhere, like control from the neck to control the flow of the electrons. So this is what we call the gate-all-around, or sometimes called FinFET, or sometimes called three-gate transistors. So what the function is, we'll still go to the IV characteristics I showed you before. So once you make it smaller, if you use the planar structures, so you cannot effectively close down the device so efficiently. So the physical limit to close this device is so-called 6 milliwatt per decade. So what it come from? It come from so-called these carriers, or electrons have this Boltzmann distribution. It's limited by physics. So the Boltzmann distribution, the physics tell you, will be K, this slope will be KT divided by Q. K is the Boltzmann constant. T is the room temperature T. So divided by Q. Q is the charge of the electrons. So if you plug this number inside at room temperature, you will get 6 milliwatt per decade. Okay, this is the fundamental physical limit. You never can break that. So if you have a loose electrostatic control like this, so this slope, you have some leak electrons, leak current, so this slope will be slowed down. But if you use this kind of structures, so then this slope will be sharper and approach this physical limit. That's the 6 milliwatt per decade. So now we use a germanium as an example to talk about what we did at Purdue. So everybody probably know this is the first transistor. It was invented at Bell Labs, 1947. And it's too important, right? Of course, in the 56, they got a Nobel Prize. It's really deserve a Nobel Prize because of this invention. Okay, this is the point contact transistor. You probably don't know. So actually, this semiconductor, this piece of the semiconductor, is not made of silicon. It's made of germanium. Okay, that's a germanium. And you probably even don't know, actually, at the beginning of the research, this piece of the germanium is made at Purdue. So the Purdue physics department, actually, that's what I learned from articles and stuff. So this 1928, Professor Horowitz joined the Purdue physics department. He built a very strong research efforts in the semiconductor crystal growth. So semiconductor at the Second War time, because of the invention of the laser in UK, so all these, solid state device need a rectifier. And the rectifier is basically a diode. So you turn on and then you need to turn off. So the turn off, the leakage current become important. So you reduce the leakage current is you need a pure semiconductor crystals. So at that time, Purdue is the place can give you the purest semiconductor crystal. That's the germanium. So that's the start of that. And Purdue is almost invented the transistor. So that's why germanium is really related with Purdue. So I really should thank this Berkeley, state of the facility and all the technical staff members, make everything working. So, and the students also work hard. This is one of the best clean room in academia in this country. So we based on the germanium materials, we are able to use the so-called e-beam lithography, dry etching, so on and so forth. We can make these small channel structures as small as 10 nanometer, even sub 10 nanometer. And it's a very, very small, and we know all our human being hairs is about 25 micron. So it's about 25,000 larger than these wires we are making. So we are not only making these, physically making these wires, we are even make a very functional, very high performance transistor based on these wires. So these are the fabricate. You can see these are the, we call the FinFET. Basically, it has a 3D Y kind of structures. We can not only make an N-type or flow the electrons, we can also flow the holes, positive electrons. So we can connect it as an inverter. So you can see, and we have the maximum gain or so on and so forth. So also all these are demonstrated. I want to, since many students here, I want to really, re-emphasize this work. It's also very interesting. So the germanium work, after the silicon replaced the germanium work is not so active anymore, but just recently, like this 10, 15 years, because the germanium has a high electromobility, also high hole mobility. So there's another bunch of groups are research germanium, also worldwide, same parallel with the 3.5 logic applications. But one of my students, want to do P-type 3.5, and he tried to eventually look at the germanium. So then we realized, actually, although everybody say, we are research on germanium, but the germanium have that one fundamental issue is difficult to make N-type contact. It's also related with the Fermi level pinning, these fundamental issue. But he just did a little bit engineering and partially solved the problem. So all of a sudden, he can at Purdue make the N-type of germanium transistor a factor of 100, even 1,000 higher than any reported in literature, way beyond. Actually, I even don't appreciate it because I do 3.5, always have a good N-type, but eventually other professors who work on germanium let me know, okay, this you are doing important work or your student doing important. So that's why some of the academic work can influence the, the whole research worldwide. Okay, so once we make all these small devices, so we suppose we can shut off the device very effectively. So we go back to this so-called substress slope. We go back to this dimension can be approaching 40 and even smaller. So then by all engineering about his PhD 3 or 4 years, you can see the substress slope from beginning first year graduate student and improved significantly down to everywhere is 100 millivolt per decade. But however, it's still 80 to 100. You never can below 60 millivolt because this is the fundamental limit. So is it able to block this fundamental limit? So this move to this third topic I want to share with you. So you have to be little bit change the device physics away from the real MOSFET. So actually this is also very active research in the past 10 years. People try to break this fundamental physical limit, propose some like a tunneling FET, NC FET is negative capacitance FET. So I use a negative capacitance FET and also use the 2D material as a channel to give you an example. So what is negative capacitance FET? This is back related with Purdue. So Professor Supridata is here. So, okay, 10 years ago, Professor Supridata and his graduate student, Saeed Halahuddin. Now he's a very famous professor in UC Berkeley. So they have a very important paper and have a high impact in the field. They propose a concept. The concept is following. So if we replace the conventional oxide, silicon dioxide, hafnium oxide, or aluminum oxide, doesn't matter, conventional oxide, with a ferroelectric insulator. If you're able to do that, so then, because at the ferroelectric switch, this regimes, if you add a half volt at your gate, you may equivalent add, because it's negative, okay, negative. So you may add like 1 volt on your transistor. So if you're able to realize this physically, so then if the negative capacitance concept is everything right, so I expect to have the transistor like this. This is the MOSFET. This slope is 60 millivolt again. So if you realize this negative capacitor FETs, so you will be expected like this, because you turn on much faster. So in other words, at the same current level, you can have much lower voltage than the conventional MOSFET. You can further scale down the voltage. That's you control the power. So this is a very beautiful concept. So we are working on that as an experimentist. Now what we realize, okay, so is now the ferroelectric materials, we still use the ALD. So we grow a particular material called the hafnium zinc oxide. Okay, this material is a ferroelectric material as I measured here. So the ferroelectric means can switch up, switch down, okay, as it's showing here. So we have the ferroelectric material here. So now the channel, now we use a semiconductor channel, but we use so-called 2D materials. So this is a very popular, research topic worldwide. 2D material back to the 2004. So the first 2D material get a worldwide attention is called graphene, and 60 years later they got the Nobel Prize in physics. So this is basically atomic layer of the carbons. Okay, there are a lot of interesting, unique properties. But however, this graphene, everything is perfect, but it is like a piece of metal. It doesn't have the band gap. It is not a semiconductor. Okay, that's the issue. So no matter how you do, you can only turn off the device a factor of 10. So you cannot factor of 5, the power of 5 or power of 10 as semiconductor, silicon, or gallium arsenide, all this we do, okay? So that's why later on, worldwide, a lot of attention is to want to look for 2D material, but has a band gap, or in other words, is a 2D semiconductor material. One of the examples is so-called MOS2, or transition metal dicoagulanides. It's a difficult name. Okay, this is a MOS2, let's say. Okay, so this is a semiconductor and also atomic layer. So the thickness is less than 1 nanometer. And my group, we also pioneered another type of 2D semiconductor material called black phosphor and the phosphorine, and recently cooperated with Professor Hu in the industrial engineering. We're even doing some other even fancy kind of 2D material. But then now we go back, just to use the popular MOS2 as the channel. So you put this as channel, 1 atomic layer or few layer. So the band gap is 1.3 or 1.8 EV, depending on number of layers. It's pretty much like a silicon. So then we look at the IV catalyst again. It's just a current voltage here. So you can see the transistor can be turned on and turned off without so-called hysteresis. It's almost like a perfect transistor. Of course, we are very interested is here how fast it can be turned off in this region. So this is a key to see if we can break this fundamental limit, Boltzmann limit, 60 millivolts per decade. So if you zoom in this area, so we have kind of professionally measured and plotted all these experiment data here. So this black dot showing like a sweep up and then sweep down. And cooperation with Professor Ashraf Alam, his group. So they use our geometry and build in these negative capacitance models and did the simulation. This is solid curve. you can see it's pretty much around our experiment data. And some of our experiment data, of course, showing it's below 60. So because this modeling and experiment, we are kind of confident. So we are kind of see this negative capacity effect in this kind of device as we predicted 10 years ago. And particular, if you compare, if you don't use the ferroelectric material, if you don't have the negative capacitance effect, so then your this slope is much slower as 80 or 100 usually you will observe in the experiment. And you can do a little bit more because this negative effect, so this is always a little bit weird. You need to think about it a little bit differently. So usually you pull down the voltage, this potential will be pulled down, but because this negative effect, if you pull down this line, actually this will go up. Okay? Because it's go up, so your current flow, you see the more problems, barriers here, your current will be lower. So that's our experiment really see this negative resistance drop. So usually your transistor will be seen like this, but this is really the negative capacity effect. And here you will see the negative dipole, some other aspect can confirm. Looks like the negative capacitance really plays some role in this device. Okay, so I think I use 3 examples, what we did at our group and cooperation with others on 3-5 logic application transistor with the materials and the germanium with very fine structures, and also these negative capacitance FETs use 2D material as a channel. And the conclusion, I think we are all proud of our university, right? So I think the Purdue is always really a front runner and the powerhouse for all these semiconductor materials and the device research. The history comes back to physics department, like the purified germanium crystal kind of work, and it now spread material science, engineer, EE, and so on and so forth. And I believe the Moore's law will be continued, although it's a slow down as this, observation is, but I think it will be continued. And by end of this year, so TSMC will really manufacturing this so-called 7 nanometer node, and the Intel next year will be 10 nanometer node. But the real dimension, so definition is a little bit different. Intel's 10 nanometer node is pretty like the TSMC's 7 nanometer node, but nevertheless, it's a keep going. And eventually, actually, I heard, right? So 5 nanometer node is pretty much ready over the development phase. So it's ready to manufacturing. So for the other 5 nanometer node, like a 3 nanometer node, more or less will be like stacked of transistors and so on and so forth. So this keeps, so there are a lot of research opportunities and, a lot of innovation research, can be doing. So I didn't cover these new type of switch. Actually, Purdue, we are doing also very well. And we have, 3 centers, one NSF center led by Professor Apazella, and one ENCO center led by Professor Jihong Chen, and also the Brian inspiring kind of centers by Professor Kausk-Loye. Just this year, have 3 centers at Purdue, so we will keep contributing to field, and hopefully our all research eventually will contribute to not only science and industry, even for our human societies. So that's my talk, and thank you very much for your attention and time.
Anyway, you distinguished yourself with a number of really pioneering work. Very impressive.
Thank you.
So, in the context of your presentation, what are you going to challenge yourself with next? What are the biggest challenges?
Oh, that's my next slide. I look at the watch. Okay. So particularly a lot of students here. So I try to answer short. Okay. So a lot of students here. So, you know, always people think Moore's law is ending, looks like ending. So what's the research about device? A little bit pessimistic, but I'm very optimistic actually. Okay. So one of the research, so for example, we are doing, so this is called a tellurium. It's again element material, but it's a very unique property. It's a hierarchy. So usually you don't have that kind of structure, but it's a one-dimensional hierarchy structure. So in my vision, for extended Morse laws, you can make the smallest transistor by just the atom level. So we are working on that. But even beyond, so because it's have this break of the symmetry is so important in the science. I gave you an example. More than 50 years ago, some of the young physicists say, okay, the physics world is not a symmetry. Okay, they got the Nobel Prize actually because of this work, right? So chemistry, the chirality is always important. And the DNA, actually, it's very interesting. It's just right-handed. It's not a symmetry. You have left-handed and right-handed. For some reason, it's right-handed in most of them. And I did more Google and I realized our Earth is rotated right-handed. And even do more, you can find our Earth is rotated with the sun, also right-handed. So let me think about, 30 years ago, Newton is puzzled by what generates the first energy to moving. So probably he will first puzzled why the Earth is rotated with the sun right-handed. It's not left-handed, right? I don't know. So by this kind of inspiring, maybe we can find something new, switch mechanism, or even, not only extend the Morse law, even can be beyond, kind of. So that's I'm thinking, I'm working, and this really need a lot of cooperations with different principles, and look at this. So that's why I think there's much more rooms in between this interdisciplinary research. Eventually, maybe help also extend the Morse law and beyond.
So what I was pointing out was Moore's law is not an empirical law, it's an industrial prod.
Yes.
And when Noyes established Semitech, whenever the 3 years was about to be up, he prodded industry to figure out a way to stay on Moore's law. And now, of course, we've reached the limit because of power dissipation and thermal, power increase, but the high power, but also the thermal dissipation is the primary limiting factor.
Yes.
I look upon your work as finding a true way to get off Moore's law with a triple threat. And the triple threat is materials, structure, and architecture.
Yes.
Now, your architecture is a solid, a physical architecture.
Yes.
What's lacking is getting off von Neumann architecture and going to neuromorphic architectures or brain-inspired architectures.
That's right.
To be able to do more with less.
Yes.
Do you have any comments on that?
Yeah, that's a very big question. That's exactly all the SRC, the new jump centers. So they are exactly as you said. So they are approaching, more, not traditional approach. And yeah, so I'm part of this center. I'm working on something, but my expertise or my special research is, it's a little bit in the material, in the low level. It's not really on the architecture or high level. Yeah. But I fully agree with you. So this is the consensus of the industry and the academia or these SRC centers, I think.
Okay. Thank you, Professor. I'm a fresh PhD student from ECE department. You have made a lot of achievements in research and academic area. Could you please share some experience for doing research, especially for PhD students, how to have a good, successful PhD career, especially for us, like a first year PhD student?
Okay, that's a good question. So I just say my experience. I think you have to have the passion. You like this work. So you're not sure just for your advisor. So that has nothing to do with your advisor. It's your research, your career. You know, you need to have the passion. And second, you have to spend, as an experimentalist, you have to spend enough time in the lab. Some people say I can work at home as a graduate student, or, you know, I don't think so. So as an experimentalist, you know, I think, you know, your really time, effort is eventually will be rewarded. And at your career development, you always have here, there, a little bit difficult. You know, your fresh PhD, you want to find a faculty job, maybe not so much ready for you to take. So, but if you have patience, you keep your goals, you have the passion, you will succeed.
It's not a question, actually it's a comment. You mentioned that Purdue is a forerunner of semiconductor research, and I've been at Purdue for 45 years. I just retired last year.
Yes.
And I'm in the College of Science. I wonder if you, in the audience, old enough to meet Professor Fan,
Yes.
F-A-N, who is the
Yes.
forerunner of semiconductor.
Yes.
He tried to compete with at Illinois, Purdue, and Purdue got 2 Nobel Prizes, and he was waiting every year, but he never get one, so it's unfair. Another person is work with similar field as Richard Feynman,
Yes.
Schwartz,
Yes.
and he at Purdue in physics
Yes.
for some time. Then he left.
I see.
So
Yes.
I would say Purdue have a very strong physics department. That is Professor Fan and Schwartz. Schwartz got the Nobel Prize with Richard Feynman.
Yes.
So I just like to make the comment to echo what you said.
Okay.
Purdue is really a powerhouse.
Yeah. Thank you
Thank
very
you.
much. Yeah. Thank you very much for your attention.